Artificial intelligence feels completely weightless. We treat it like it's made of language, image, and pure thought, floating effortlessly inside a digital cloud. But that cloud has a massive physical footprint. Right now, hyperscalers are spending $690 billion on the physical infrastructure required to keep those digital systems running. Behind every prompt you type sits a colossal, punishingly heavy reality: millions of pounds of advanced hardware, massive cooling systems, and millions of miles of cables. None of it is conjured out of thin air. The race for AI supremacy is a contest over the physical extraction of the Earth itself. When we think about tech bottlenecks, we usually point to advanced chip designs from companies like NVIDIA or TSMC. But a chip blueprint is completely useless without the raw, volatile structural materials required to physically build it. To make generative AI exist, you need ultra-pure silicon for logic processing, specialized compounds like gallium nitride for high-efficiency power management, and entirely different materials for rapid data transmission. Yet the immediate threat to the global infrastructure boom is located outside the silicon processor. The entire trillion-dollar AI ecosystem possesses a systemic vulnerability in the massive physical network connecting those servers together. Generative models require parallel processing. To train a single model, thousands of graphics processors must talk to each other simultaneously with absolute zero latency. To achieve that zero latency, a modern AI server rack requires up to 36 times more fiber optic cable than a traditional cloud server rack. To make that fiber optic glass transmit data at lightning speeds without degrading the signal, manufacturers rely on an irreplaceable chemical dopant called germanium. This hard, crystalline mineral grounds abstract network speed into a tangible object. You cannot route the massive amounts of data required for AI without it. Because the global tech industry relies almost entirely on this specific chemical dopant to build networks, it has created an immense structural choke point. Geographically, germanium extraction is highly concentrated. Roughly 60% of the world's raw production happens within the borders of China. This chart breaks down the actual control over that supply chain. You can see the 60% share of raw mining on the left, but the real leverage is on the right. When we look at refined output, China's monopoly jumps to an overwhelming 82%. An obscure rock has allowed a geopolitical rival to hold Western tech giants hostage. The most complex digital systems on Earth are only as strong as their weakest physical link. In response to this freeze, Western allies have launched a massive, coordinated counteroffensive to circumvent the export controls and secure their critical supply chains. Success requires midstream capacity, the high-end industrial facilities needed to refine raw rocks into pure tech-grade minerals. To bypass the monopoly, the U.S. Department of Defense has injected billions of dollars into domestic projects designed to scrape trace germanium and gallium out of existing operating zinc and alumina smelters. The processing of obscure minerals has become a matter of absolute national security and systemic survival. In a twist of deep irony, engineers are now using generative AI itself to solve the mineral crisis threatening its own existence. The Department of Energy is deploying AI-powered prospectivity forecasting models to scan thousands of square miles of geological data. These models help geologists discover unconventional mineral deposits in record time. AI is actively hunting the elements it needs to survive. The era of peaceful, globalized technological interdependence has been replaced by a reality of aggressive techno-nationalism. The ultimate winner of the AI boom will be the nation that controls the Earth's bedrock. The future of intelligence is entirely geological.